back to this. Okay, great. So probability is really like an interesting concept. It's trying to predict something that could happen or describing the prediction of something that can happen. Your book even kind of goes over the fact that it's really mainly due, like this whole concept is mainly due to gambling, right? I mean, trying to figure out what's going to happen whenever there's an experiment, the outcomes of the experiment, or the probability of the experiment happening. Yeah, it's not that big of a deal. The main thing, let's just kind of go with the book so I don't step over my toes here. But it defines probability as the probability of an event is the proportion of times the event occurs in the long run as a probability experiment is repeated over and over and over. So it then defines, a probability experiment is one in which we do not know what an individual outcome will be, but we do know how a long series of repetitions will come out. Okay, so let's look at a basic probability experiment. Okay, so let's start there. Probability experiment. And I'm gonna flip a coin. Okay. Flipping a coin. Now I know there's always some smartass that says it could land on the side, but we're gonna say it can only land on heads or tails. Okay. This would be the experiment. And the idea or the probability outcomes are either going to be heads or tails, right? So those are the two outcomes that we can have. And the idea is that if you flip this over and over and over, you would see the true probability occur, right? If I just flip a coin a few times, I'm probably not going to get 50-50, right? If I flip a coin 10 times, which I'm not going to sit here and do that, you're more than welcome to do it at home. But like if I flip it 10 times, I'm probably not going to see five heads and that's just not really typically what happens when you do that. Hold on, there we go. Okay. There we go. So if I flip a coin 10 times, I'm not going to see 5 heads and 5 tails. It's probably going to be something more like, 4 and 6, or maybe 3 and 7. It doesn't matter. But the idea is that if you do this over and over and over again, the probability of heads, let's stick with heads, is 0.50. Okay, 0.50. So it's the idea that if you flip this coin over and 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 over again, you'd wind up with half the times 0.50, half the times would be heads, and we know the other half would be tails. But it can't be from just one flip or two flip, right? One flip, you're only gonna get one or the other, right? I mean, so but it's if you do this over and over and over, what would happen? Okay, and it talks about that on the top of page 205. It's called the law of large numbers. And this is kind of, if you guys took that test, like I had some kind of short answer questions. A law of large orders would be a good short answer question. Like, explain law of large orders or large numbers, give me an example of it, something along those lines. But it says, the law of large numbers says that as a probability experiment is repeated again and again, the proportion of times that a given event occurs will approach its probability. Okay. So like if we're rolling a die and, we roll a die over and over and over and over again, and we just look at the number of times the number 2 pops up, right? Well, we know that 2, if it's a fair die, it's got a 1 in 6 chance of happening, right? So what would happen is if you roll a die over and over and over again, you'll see eventually it would get closer to 1/6, which is like, hold on, let's see what 1/6 is in decimals. Calculator 1 divided by 6, 0.167, if you round. So you'll see that around 0.167, eventually we get closer and closer to 0.167 of the 2 popping up, when you roll the die. Okay. So with probability models, so I'm going to kind of keep going with the book. To study probability formally, we need some basic terminology. The collection of all the possible outcomes of a probability experiment is called a sample space. So a sample space contains all the possible outcomes, right? So if we're looking at this coin experiment, we've got heads and tails. That would be the sample space. That's the only thing that can happen whenever we flip a coin. If we roll a die, we can get 1, 2, 3, 4, 5, and 6, right? Your book goes over, describing sample spaces, like on that right underneath it. Like one of the questions is selecting a student at random from a list of 10,000 students at a large university. Well, each possible outcome is the selection of the student, right? So it says each of the 10,000 students is a possible outcome for this experiment. So the sample space consists of 10,000 students, right? But then, like, if you're selecting a simple random sample of, say, like 100 students out of the 10,000, the sample space consists of every group of 100 students that could be chosen from 10,000. So every possible simple random sample of size 10,000 or of 100, it's gonna be a lot for that example. So the sample space really is the total number of outcomes that could happen from the experiment. It'll look like a deck of cards. I like talking a lot about deck of cards. So if you have no idea about a deck of cards, I'm going to kind of run through it real fast. But we've got 4 suits, right? We've got clubs, hearts, diamonds, and spades, right? There's 52 cards. So you got to think, if the probability, what's the probability space when you look at suits is only 4 things, right? You can get a club, a heart, a diamond, or a spade. But then if I said, well, what's the probability of drawing like a single card? Well, it's all 52 cards would be the sample space. But then there's 52 cards, so there's 13 cards in each suit, right? Ace, or depends on where you want to start. Either ace up to king or 2 up to ace. It depends on what you're looking at. If you don't want me to use this sample or that cards at all, let me know. But it's kind of fun playing with cards in this section because there's a lot of different ways you can change the probability, right? If I said, well, what's the probability of choosing a club? That's going to be a lot different than what's the probability of choosing a 10 of diamonds. So it's kind of fun playing with cards. Okay. Yeah, the 2 joker, the high, low, and all that stuff. So let's keep going with just definitions. And really what's going to happen is this first part, 5.1, lays the foundation for the vocabulary we're going to use throughout. So an event. So we had probability experiment is, like flipping the coin. An event is an outcome or a collection of outcomes from a sample space. So an event is the actual outcome from a sample space. Okay, so event, you'll hear me use these words: probability experiment, event. The law of large numbers, I won't necessarily use that often. It's just we have to understand, look, like with cards, if we flipped over cards, if we shuffled the deck, flipped a card over, and shuffled the deck, put that card back, flip the card over, and all that fun stuff. If we do that over and over again, you'll see clubs will wind up happening about 1/4 times, really close to 1/4 of the time. That's what the law of large numbers means. And then your book goes over the probability model. So for a probability experiment consists of a sample space along with the probability for each event. So if A denotes an event, the probability of A is denoted by P of A. So the probability model, and we're going to do a basic one here. Probability model is the experiment for a probability model for a probability experiment consists of a sample space along with the probability for each output or each event. So if we looked at flipping a coin, okay, flipping a coin, the sample space we know is either heads or tails. Okay, that's the sample space. So the probability model is going to include the probability for each of them. So the way we would denote this is capital P. This means the probability of H. So this would mean the probability of heads. Okay, the probability of heads. And we know the probability of heads is 1/2, right? For flipping a coin, because you've got 1/2 chance of heads and a 1/2 chance of tails. So the probability of heads, now I'm going to tell you, I like writing it as decimals. And that's not an algebra thing at all, right? In algebra, we would leave fractions. But in statistics, we use decimals a lot more than fractions because it makes more sense to say something, is 0.16 chance of happening compared to like 1/6. Now, the probability of tails would be the same exact thing. So 0.5. This is my probability model because it tells me the probability of each event occurring, the flipping of heads and flipping of tails. So it gives me the probabilities of each one of those occurring. Okay. Question? That makes sense, Laura? Yeah, good. Okay. So your book talks about, let's say, a fair die is rolled. What am I gonna do? It's the find the probability of if we had like a deck of cards and it was shuffled and it was a fair deck of cards, probability of flipping an ace over. Okay, so we shuffled up the deck of cards, we put it there, and we want to know what's the probability we flip the ace over. So I need to know a few things, right? Now in this situation, I've either got aces or non-aces, right? In my deck of cards. I'm not worried about like the king, 10, 9, doesn't matter. You're either an ace or a non-ace. So the way we denote that is you've got ace, and then if you put a line over it, it means not ace. Okay? So that means not ace. Okay. So I'm going to write these as fractions before we put them in decimals to show you where it's coming from. Now I know, remember, there's 52 cards total. And I know 4 are aces, right? Ace of spades, diamonds, clubs, hearts, right? So 52 cards total, 4 are aces. So if I want the probability of an ace, now I'm going to do the model as well, just for fun, but probability of ace would be 4 out of 52, right? Makes sense. I'm going to write that as a decimal. So clear, let's say 4 divided by 52. Oh, I'm going to round it. So that's going to be 0.077. We'll do 3 decimal places. Now the probability of drawing a non-ace, well, 52, the other 52 cards out of except for those 4. So that's going to be what, 48 out of 52, right? So because the other 48 cards are not aces, right? 48 divided by 52. So that's going to be 0.923. Okay. Now I asked you to find the probability of flipping an ace over. This is that answer. Okay. Now your book might write it as a fraction at first, but I'm going to tell you in the end, we're going to use decimals. This though is the entire probability model because it tells us the 2 things that could happen. Okay. It tells us the 2 things that can happen. And notice when you add these 2 probabilities, you're going to get 1 because it's everything that can happen. In a model, it's everything that can happen, okay? Everything that can happen. I'll explain that here in a minute. I think your book kind of does this out of order. You guys get this? So if I want the probability of something occurring, it's just the number of times it can occur over the number of outcomes, right? There's 4 outcomes that are aces. There's 52 outcomes total. So 4 out of 52, that gives us the 0.077. Okay, cool. Then it goes on to divide probability, which I think it should have done from the beginning. Computing the probability of an event. So this is on page 207 now. It says, now look, the probability of an event is always between 0 and 1. And this is why I use decimals. Okay? Probability of an event occurring is always between, and including, I should say, between, like, so it can be 0 and it can be 1. 0 and 1. So the way you kind of write it, like if we had some event A, the probability of that event A occurring is always between 0 and 1. It has to be. Okay. Of course, like the probability of a 0 would mean that there's no way possible that that could occur. So like if we're looking at flipping a coin, there's no way that I could flip a coin and get the number 2. That doesn't make sense, right? So that would, if I wanted to say the probability of getting 2 from a die or from a coin, it would be 0. But then like the probability of getting, you know, let's say just the probability of getting a number when you roll a die, right? That would be 1. Because you're definitely going to get a number. You don't know what it is, but you're definitely going to get a number. Okay. I hope that makes a little sense. So yeah, it kind of goes over that. A cannot occur, then probability of A equals 0. If A is certain that it's going to occur, it's the probability of 1. Okay. And then it goes over kind of plotting or finding probabilities. Yeah, that's not a horrible example. We might get to that here in a minute. Yes, okay, good. So let's do a basic one that your book goes over because it kind of uses it for the next example. It says a family has 3 children denoted by, so we've got B for boy, and then, G for girl. Okay. And we can denote the genders of these children from oldest to youngest. For example, so, GBG means that the oldest child is a girl, the middle is a boy, and then the youngest is a girl. There are 8 possible outcomes. So yeah, if you have 3 kids, there's going to be 8 possible outcomes, right? And we'll kind of model this as we go. So we've got B, B, B. We could have all boys, right? And then we could have 1 girl. I assume that's the youngest, the way they're talking, right? Then, so if we had 1 girl, we could have 1 girl 3 different ways, right? Does that make sense? And then we could have 2 girls, right? So we could have a boy and 2 girls. And then we could have a girl, boy, girl. Or we could have girl, girl, boy. And then we could have all 3 girls, right? I think that's all the outcomes. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So these are all the different ways. If you have 3 kids in order, right? You had 3 kids, so I guess no twins that pop out at the exact same time. But if you have 3 kids in order, these are the 3 different ways you could have 3 kids with their genders. So, so the question says, what is the probability that there are 2 girls? So now think about this. This is our sample space, right? Sample space. I got to make sure I'm using the right terminology. Yeah, these are all the possible outcomes, right? So I've got 8 different outcomes. And the question says, what's the probability that there are 2 girls? And it should say exactly 2 girls, because you could say that these 3 is 2, but well, we'll say exactly 2 girls. So probability 3 girls. Oh, I'm sorry, 2 girls. 2 girls. So let's see here. I'm going to just underline these. There's 2 girls, 2 girls, 2 girls, right? Well, we're not going to do all 3, right? Because we're going to consider that 3 girls. So there's only 3 that contain 2 girls. You see that? So then the probability would be, let's say 2 girls. So the probability of 2 girls would be 3 out of, now we know the total space is 8. So 3/8, okay? And I'm going to use my calculator. I'm going to start writing this as a decimal because I wish they would do that from the beginning, but I didn't write the book and make all the money. Okay, so 0.375. Notice this is between 0 and 1, because probability, when you do this correctly, this probability will always pop out a number between 0 and 1. Okay, now the next question is, what is the probability that all 3 children are of the same gender? Yeah, all children. Same gender. Okay, so all the children being the same gender, that's 3 boys or 3 girls, right? So the probability, I'm just going to say all, for all are the same, is going to be 2 out of 8, right? Still 8, because there's still 8 things that could happen. And we know that's 0.25. That's a quarter, right? So you have a much better chance of having 2 girls. Now I'll tell you the 2 boys is the same, right? Because there's kind of symmetry going on here. But you have a much better chance of having like 2 girls or 2 boys than having all 3 of the same gender. with three, which is crazy because I feel like you find families that have like 3 boys or 3 girls, and it's more common than not. Okay. Questions, comments, concerns. This is a good example. This is a good example of kind of creating, like, let's think if we had something similar to this. I'll try to make one up that's similar. It's not too crazy. Oh, come on. Where's the boom? Okay. Something similar to this would be, well, very similar. Let's say we flipped a coin 3 times, right? So flip a coin 3 times. And I win if I get 1 head. Okay? Out of those 3 times, right? Only 1 can be head. What's the probability I win? Well, let's see. Okay, so I've got to flip it 3 times, right? So let's think of all the outcomes that can happen if I flip a coin 3 times. I could get head 3 times, right? Which I would lose, okay, right? Because I only need a 1. I could get heads, heads, tails, heads, tails, heads, or tails, heads, heads, right? And in all 4 of these situations, I lose because I can only get 1 to win. So now I could get 2 tails, which is really going to give me the win. So 2 tails and then a head. Tails, head, tails, or heads, tails, tails, right? And then lastly, I could get 3 tails. And this is at 1, 2, 3, 4, 5, 6, 7, 8. It's the same as boy and girl, right? I mean, because they're the same chance, everything has the same chance of happening. But in my question, it said, look, I'm going to win if I only get 1 head here. So there's 1, 1, 1, right? So the probability, I'm going to just say for W, for winning, is going to be 3 out of 8, which we know that's 0.375. I've got about a 37.5% chance of winning in this situation. Okay. Okay. Computing probabilities. Oh yeah, involving settlement. Okay, cool. So I'm going to steal this right from the book. This is on page 209 in the book. And it's example of 5.6, because we can create probabilities that come from samples. So not necessarily like this where we just got a very defined experiment, but if we looked at their example, so there are 10,000 families. So they sampled 10,000 families, and they're categorized by their type of house. So we own a house, own a condo, rent a house, or rent an apartment. I guess you can't rent a condo. So rent a house or rent an apartment. Now this is just a crude little Excel sheet here. Now it turned out 4,753 owned their house. 1,478 owned a condo. 912 were renting a house, and 2,857 were renting an apartment. So if you add all these up, they're going to add up to 10,000, because those were, I guess, the 4 options going on. I assume they are, because there's definitely a lot more options than just those 4. I'm going to add these up real fast. 4,753 plus 1,478 plus 912 plus 2,857. Yeah, this adds up to 10,000. Okay. So these were the only 4 options given there. So the question states, what's the probability that the sampled family owns a house? So A says the probability of, I'm going to say owning a house, OH. Okay. Well, we know 4,753 replied that they owned a house out of 10,000. Okay. So the probability of owning a house is going to be 0.4753. Okay, 0.4753. Notice I am not writing this as a percentage. And I know that's kind of a goofy thing, but remember, we said probability is always between 0 and 1. So you leave it as a decimal. In statistics, you leave it as a decimal. Now, if you were kind of explaining it to someone that wasn't taking a stat class, you would say, oh yeah, there's a 47.53% chance that you own a home, right? If we were sampling like in a town or whatever. But for probability in the stat class, we would leave it as 0.4753. And it's a goofy thing, but it's just how it is. We don't deal with really percent notation moving forward. And then the next question says, what's the probability that the sampled family rents? Well, we've got two rental options here, right? You could either rent the house or rent an apartment. So if we want the probability of renting, we'd have to add both of those together. So renting the house plus the probability of renting the apartment, okay? And we know the probability of renting the house is 912 out of 10,000. Plus the probability of renting an apartment is 2,857 out of 10,000. So I'm just going to use my calculator. And I'm going to say 912, clear, 912 plus 2,857. So that turns out to be 3,769 out of 10,000. 3,769 out of 10,000. So it winds up being 0.3769. That's the probability that rent, right? Not rent a house, not rent an apartment, but rent, period. Okay, 0.3769. Question? You getting that on the other side there, Zach? You hear Zach and Coulter?
Yes, I am.
Make sense?
Yeah.
Awesome. I'm telling you guys, like, to me, this is the fun stuff. Like, stats can get really kind of in the weeds and really weird and theoretical, but this is more of the fun stuff. And we'll get to examples of like when you should gamble, when you shouldn't gamble. We'll do some fun stuff like that. Okay. But you got to learn kind of the foundation before we can really get to the fun stuff. Okay. Then your book goes over like unusual events. It says, as the name implies, an unusual event is one that is not likely to happen. Oh, I see what you're saying. Hey, give me a second, Zach. Hold on. That's weird. So it's a little better if I go that way.
Yeah, your chat is on the side. That's what's.
Oh, did it skew it when I did that? Okay, hold on. Let me make the chat go away. Is that better? Okay. Okay. So yeah. So anyway, so an unusual event though is one whose probability is really small. Sometimes people use the cutoff of 0.05. That is, they consider any event whose probability is less than 0.05 to be unusual. But there's no hard and fast rules about this. This is going to come into play later on, not really in this section, but we're going to talk about that a little. So if an event is less than 0.05, we consider it unusual. It's not like an outlier. It's not like we should throw it out or we should get rid of it. It's just that we kind of need to think of it as being, I spelled that completely wrong. Unusual. Okay. I know. What did I do? Unusual. Seems it's just a weird word. You don't use that often, but unusual. So it's just weird. I mean, so like, oh, this is totally true. This next example says in a college of 5,000 students, 150 are math majors, right? So we want the probability of math majors. Well, we know there's 150 out of 5,000 are math majors. Well, that turns out to be 0.03. So, we're like, yeah, that's kind of unusual. Maybe if you're at the college, you're maybe thinking, well, how can I get more math majors? Or, hey, should we just cut that department so we can save money? Whatever. But in the end, the 0.03 is that it's kind of just an unusual number. That cutoff, we're going to consider this a cutoff number for something later on. And for this part of for this chapter, even it doesn't matter that it's a cutoff, but that 0.05 kind of comes back into play later on. It's kind of foreshadowing, actually. Okay. And then, yeah, your book goes over the approximating. So, yeah, the law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that a particular outcome occurs is likely to be close to the true probability of the outcome. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. So it gives this example with the Center of Disease Control. It says the CDC, which is definitely in the news lately, the CDC and prevention, or it's actually the Center for Disease Control and Prevention, that's not the CDC, Center of Disease Control and Prevention, reported that in a recent year, there were 2,046,935 boys and 1,952,451 girls born in the U.S. Approximate the probability that a newborn baby is a boy. So, like, look, it's just saying if you add those together, and your book is doing this, I'm not going to do this at all, but it turns out that the proportion from that year, actually, we'll do this. So we had 2,446,953. This is boys, right? Girls were a little less, so 1,952,000.
It's 935, not 53 for boys.
Not 35. Oh, okay. And then 451 for girls. Yeah. So approximate the probability that a newborn baby is a boy. Well, so if we wanted the probability of a boy, we know we're going to take 2,046,935 and then divide them by those two added together. Well, the book adds them together for us, so it's 3,999,386. Okay. And when you do that, the proportion turns out to be, the probability for this year of it occurring is 0.5118. Okay. Now we know that it should be half, right? So that's why we use the approximation. The probability of having a boy based on this experiment in a way is roughly 0.5118. Okay. This is, the approximate symbol. Approximately that. Now, and we don't know what the true number is, right? It should be 50-50, right? Or maybe it's not 50-50. I don't know. Maybe it shouldn't be 50-50. But since we don't know the actual probability, it's not like a die, right? We know the actual probability of a die, or flipping a coin. So because we don't know the actual, we can make an inference on the whole probability. Well, we know the probability of a boy being born. Yeah, it's really close to 0.5118. Okay, that's what it's saying. And then it talks about examples or simulations. So in practice, it can be difficult or impossible to repeat an experiment many times in order to approximate a probability with this method. In some cases, we can use technology to repeat an equivalent virtual experiment many times. Conducting a virtual experiment in this way is called a simulation. Most statistical software packages and many calculators will perform simulations. I think the TI will. I'm not going to show you how to do it. It's not a big deal. But realize this happens all the time. Like every week in the NFL, they do these simulations on if these two teams played 10,000 times, who would win, that game. They're just saying they have some, computer generated software or Madden or whatever, and they just get it to play over and over and over again. And it gives you a probability of who will win. Because think about it, like if they're using all these stats from the past to predict the outcome of the winner. So if they had two teams play each other, 10 times and one wins 7 out of those 10 times, probably a good chance they're going to win. That's kind of that's kind of how the betting works too. So then But then if they expand it to like 10,000 and they notice, hey, it's getting closer to like the middle, like 5,000. So that little, that just running that simulation 10 times might not have shown you a better approximation. It gave you 7. Well, then you go to like 100 times, and let's say it's more like, 100 times, let's say it was like 53. Oh, well, that's closer, right? It's getting closer to whatever that true approximation is as you increase the number of simulations. I'm not worried about you knowing how to do a simulation or even like the definition of simulations. That's not really the curriculum for this class, but it is kind of interesting. So for homework, this is 5.1 now. So 5.1. Homework. And yeah, I'll tell you, this is important. This homework's important because it's getting these definitions and the terminology down, mainly so you can fix me and correct me whenever I say the wrong thing. Let's do 1 through. These don't take long at all, guys, actually. Let's do 1 through 42. Oh, yeah. I want you to look at 45, 46. This is kind of, it's extending the concept. It's okay if you don't get these correct. Actually, I'll probably do all these. I don't know why I'm doing them one at a time. Yeah. Let's do 45, 6, and 7. Okay. It's about rolling 2 die. So 1 through 42, and then 45, 46, and 47. And that's, if you want to know the page, I think it starts on 213. Excuse me, page.
213 is where it starts.
Yeah, 213. So page 213, 5.1, 1 through 42, and then 45 through 47. Okay. What time do we get out here? 10:40, that's right. We'll get to 5.2 at least. So 5.2. 5.2 is going to bring in rules. And I kind of mentioned one already, but we're going to talk about a few other ones. But there's a lot of rules that come with probability and the notation aspect of probability as well. So 5.2 is going to go over some new rules. And at first, it goes over the addition rule, I believe. Yeah. Well, I'm going to start giving you names. So the first thing it talks about is a compound event. And this was like earlier we said something like if you rent, right? In a way, if you rent was a compound event because you could rent a house or you could rent an apartment. That's considered a compound event. It's when a compound event is an event that is formed by combining 2 or more events. 2 or more events. Now, the definition, though, you use this or statement. So the probability, if we had 2 events that occurred, you would say A or B. Okay. And this means the probability that either A or B occurs. Pretty straightforward. So the probability that either A or B occurs. So your book gives you, making sure this, I don't want to jump forward too much and then come back. There we go. This is the first time for me to teach out of this book. I've taught online with it. It wasn't my favorite thing in the world, but I like the book. Teaching online was the not favorite part. The book was fine though. Yeah, okay, cool. So the probability of A or B occurring. So the book gives an example of table 5.2 presents the results of a survey of which 1,000 adults were asked whether they favored a law that would provide more government support for higher education. In addition, each person was asked whether he or she voted in the last election. Those who had voted were classified as likely to vote, and those who had not were classified as not likely to vote. And it gives us this table. I'm going to write this out because we're going to do it. So we've got really kind of 2 groups up here. We've got the likely likely to vote, and then not likely, right? Gotta get that in there. And then we've got favor, oppose, or undecided. Favor, oppose, or undecided. And then those, so those that had voted and were in favor of additional support to higher ed, there was 372 in that group. Those who voted before but then opposed additional funding were 262, and those who just weren't sure but they did vote last time were 87. Okay, and then those that didn't vote last time but then were in favor of it were 151. Those that opposed it but didn't vote last time were 103, and then 25 didn't vote and were just undecided on the issue. Okay, now this is called a contingency table. Okay. If categorizes people with regard to two variables, okay? So contingency table, right? Now here's a few rules about these contingency tables is nobody can be in more than one like square, right? You can't have someone that voted or that didn't vote that favors and opposes, right? You would have to choose. Like, so whenever I ask, if I'm the surveyor and I ask these questions, they've got to wind up in one of these 6 bubbles, right? And that's an important part about the contingency table. You got to wind up in a bubble somewhere, okay? And you can't be in more than one bubble for a contingency table to work. Okay, so it says compute the probabilities by using equally likely outcomes. What is the probability that a randomly selected adult is likely to vote and favors the law? Okay. So this is a probability. They likely to vote and favors the law. Now, I am not a fan that they just told you the or thing and now they're going to give you and, because and means 2 different things. So this is actually an or statement. What's the probability they're likely to vote? Oh, no. I'm sorry. It's an and statement. Likely to vote and, yeah. Okay. Why didn't they define the and? Whatever. Okay. So what this means is it's likely and favor. Okay. So likely and favor is right here. Yeah, 372 out of what was it, 1,000, I think. Yep. So 0.372. So the probability that we're likely and we favor is 372 out of 1,000, right? And then it says, what is the probability that a randomly selected adult is likely to vote? Now, this is really the or statement going on, okay? Because I want the probability that they're likely and they favor it. I'm going to use LF just to shorten it. Or they're likely and oppose it. Or they're likely and they're undecided, right? I need all 3 of these here. So I've got to add them all up. So this would be 372 out of 1,000 plus 262 out of 1,000 plus 87 out of 1,000, right? Add those up. Actually, I'm going to steal them, what the book says. It says 721 out of 1,000. So 0.721. So the probability that, or the likelihood that someone votes, given they're from this population, is going to be 72.1%. So 0.71. Okay. I'll let you see that's not a big deal. Then it says, okay, now we're going to use the same table, but I'm going to bring in another piece of paper So the next question, it goes on a little bit and it says, hey, what's the probability that a person is likely to vote or favors the law? Likely to vote or favors the law. Okay? So now think about this. If you're likely to vote, you're going to be in this column right here. All three of these people. This whole group, right? And if you favor it, you're in this group. Okay? So what that means is we've got to add up each of those four cells. That's going to tell me if you're likely to vote or you favor the vote. Now, you wouldn't count these people twice, like, because really, look, this is all the likely people that are voting. This is all the people that are favoring the vote, right? But when you add those up, you wouldn't add these together twice. So the answer to this would be 372 out of 1,000 plus 262 out of 1,000 plus 87 out of 1,000. That would be the probability that they're likely to vote, right? Plus, now we've already added the 327 here, so we just need to add the 151 out of 1,000. And you wind up, now I'm stealing this from the book, you wind up with 872 out of 1,000. So 0.872. Okay, 0.872 would be the probability that you're likely to vote or you favor the policy. Yeah, okay, cool. So now here's the general addition rule. I was wondering when I was going to come into this. So here, circle that. The general addition rule. And it says the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And I'm going to stick to this for a minute, and we're going to go over something called Venn diagrams. I don't see where your book goes over this, but it is going to be the easiest way to explain this general rule of addition, okay? It's going to be the easiest way to explain this general rule of addition. Okay, now a Venn diagram, so I'm going to come back to this, but I'm going to really go over Venn diagrams in depth. I might just spend the next 20 minutes talking about Venn diagrams, okay? A Venn diagram is a visual representation of the entire sample space in a rectangle, okay? We're going to use rectangles, we're going to use bubbles. Every single thing that can happen is in that bubble from whatever we're going to talk about, okay? So let's say we had 100 people. And let's say we had 60 males and 40 females. So for whatever reason, we chose these 100 people and there were 60 males and 40 females. Well, that wouldn't be a good example. Hold on. No, let's think of a better example here. No, I'm going to, guys, scratch that. That was me trying to think of something off the top of my head. Didn't work well. Let's say we've got a bubble of people here. No, we can do it like this. We can do the whole female male thing, okay? In this bubble, we have all the males, okay? So that means inside the bubble is male. Outside of this bubble, though, are going to be all the females, okay? And then we're going to, we sampled males and females, and we asked them, do you own a cat, okay? Do you own a cat? So let's use, I'll use a different color. Okay, do you own a cat? Now, I need you to realize we have really 4 groups going on here. Okay? We have 4 groups going on here, and I'm going to label each one of these. So this is group 1 is right here that's just not in one of the circles. Group 2 is in this part of the circle. Okay? Group 3 is that overlap, and group 4 is just inside the cat circle, but it's also inside the female circle. Okay? So group one really correlates. Now look, they're not males, so they're females. They're female. And since they're not in like this circle for the cat is if you own a cat, okay? So since they're not inside this bubble, circle one is female that do not own cats. That's this group. You know, we could do like, that's this group all right here, okay? That's that group. Group two, now look, group two is male, right? Because they're in the male bubble. But they're not in the cat bubble, so they don't own a cat. Okay? So that second group right there, I'll use, we'll go this way. Why not? That group right there, they're male, right? Because they're not, the females are out here and the males are in the circle. But they don't own a cat because they're not in the cat bubble, okay? Three, now three is in the male bubble, right? So it's going to be male. It's also in the cat bubble. So male that owns a cat, okay, or more than one cat. And we'll use like up and down lines. That group right there is the group that is male because they're in the male bubble still, and they're also in the cat bubble. So they're male and they own a cat. And then lastly, four, now four, look, they're not males because they're not in the male bubble, so it's female. And they're in the cat bubble, so they own a cat. You guys see that down there? Yeah. So females that own a cat, we'll use like sideways here. It doesn't really matter. I just need you to see that there's four distinct sections in this diagram. And look, again, you can only be in one of these bubbles. Like I'm a male and I do not own a cat. So I would be in this bubble right here. There's me, okay, hanging out in the bubble. Lori, do you own a cat?
I did.
You did? Oh yeah, that's why you didn't. So right now though, you don't own a cat. So Lori is gonna be in this bubble right here, right? Wait, no, she's out here. She's a female that doesn't own a cat. So she's sitting there. Zach, do you own a cat? Zach does own a cat, right? Haven't I seen the cat? Zach, are you there?
I have a cat. I have a couple cats.
Perfect. So Zach's male and he owns a cat. So he's going to be right here in this bubble. Does that kind of make sense? Coulter, do you own a cat? I'll give you a second to respond, Coulter. Hit that mute button. Oh, he might have just signed in.
There he is. Yes.
Oh, he does. Okay, perfect. So Coulter and Zach are hanging out in the male cat ownership bubble. Okay. Hopefully that kind of makes sense. So this is a Venn diagram. So Venn diagrams are going to be just groups. It's a way to group. It's a way to group people. That's all it really is, and it's a visual way to do it, and it's kind of nice because it'll lead me back to this. I'm going to use another example. Oh, that's okay, Coulter. No, that's no big deal. So let's say, let me a second. Let's say, let's say I sampled 1,000 students on campus. So I'm going to do this one with numbers, not really with probability. And it turns out now it's kind of nice on our campus because you're either a freshman or a sophomore, right? So when they responded, it turns out that there's, let's say 600 freshmen, which means there's 400 sophomores, right? So freshman, sophomore. And then I asked the question, do you like Zoom? Very general, broad question. Do you like Zoom? And turns out that let's see here, see if I can get this a good one. Do you like Zoom? Yeah. So freshmen?
Freshmen do.
Well, now let's say out of those 600 freshmen, 250 said they liked Zoom. And then out of the sophomores, let's say just 100 like Zoom. Let's see if I can do this one. So I had to think of the bubbles. I'm going to think of how to draw these bubbles. I'm going to put the freshmen in this bubble. So the sophomores are outside of the bubble, right? Does that make sense? Now I've got to make the Zoom bubble now. So this will be the people that like Zoom, okay? That's the people that like Zoom bubble. And I'm going to fill this in with what we know here from our response. So the freshmen that like Zoom are 250. So that's right here. There's 250 students, freshmen, that like Zoom. So that means, look, this part of the bubble would be freshmen that don't like Zoom, right? And I know if there's 600 freshmen total, 250 said that they like Zoom. That means what, 350 didn't like Zoom, right? So that's how my freshman bubble would be split up. So my freshman bubble, 250 like Zoom, 350 didn't like Zoom. That makes sense? So the freshman that like Zoom is 250. So now here's freshmen. Here's the overlap there would be the freshmen that like Zoom, right? Because here's my Zoom bubble. So there's only 250 that were freshmen and liked Zoom. So they're here. But now there's 600 freshmen total, right?
Okay.
So there's got to be, does that make sense? So
Yeah.
there's 600 freshmen total. So there's got to be 600 freshmen, 600 respondents in this one bubble. So freshmen now outside of this are sophomores, right? So sophomores are out here. Now, sophomores that like Zoom were only 100. So there's 100 students in this bubble, okay? Which makes sense. You add these together, there were 350 that like Zoom, right? But 100 students that are sophomores like Zoom. Well, I know that there's 400 sophomores total. So there's 300 out here, right? 300 students out there. So there's 300 students that are sophomores that didn't like Zoom because they're not in the Zoom bubble. 100 sophomores that like Zoom. 250 that were freshmen that like Zoom, and 350 that were freshmen that didn't like Zoom. Okay? Kind of cool. Okay? Now I'm going to use this and we're going to go over, actually, I'm going to write this with probabilities now. Okay? So same thing, because typically you write Venn diagrams with probabilities. Now this is nice. Remember, it was 1,000 students. So this would be 0.35 for this part of the bubble, right? 0.25 for the middle part, 0.10 out here, and then 0.30 out there, okay? And we're going to define what each one of these bubbles are. And I'm going to write these in math terminology, okay? I should say stat terminology. So the probability that we're a freshman and we like Zoom. I remember here's freshman, here's Zoom. That's going to be 0.25, right? That's the freshman Zoom overlap, right? The probability we're a freshman and we don't like Zoom. Now look, your book brings this up. Remember I put the line over it? They use a little C in the exponent. That's a C right there. And that means complement. So it really, what this is saying is you're a freshman and instead of liking Zoom, you're not in the Zoom bubble, okay? You're the complement of that. We'll go over the complement here in a minute. I'm kind of getting ahead of myself. But this would be 0.35, okay? Because this is this group right here. It's the freshmen that didn't like Zoom. They're not in the Zoom bubble, okay? And if I wanted the probability that you're a sophomore and you like Zoom, this would be, now the sophomore is not in this bubble, right? And if you like Zoom, well, that's only 0.10, right? There's 100 sophomores that like Zoom, so 0.10. And then lastly, the only other thing you can be is a sophomore and you don't like Zoom, so that's going to be 0.30, okay? Now, but there's a lot of other probabilities going on with this, right? The probability that you're a freshman in general, right? If I want the probability you're a freshman, I just had to add these two parts of the freshman bubble up. So 0.3 plus 0.25 is 0.60. We knew that, right? But notice those add together. Probability that you're a sophomore. Now remember, sophomore is anything not in this bubble, right? So 0.30 plus 0.10. So 0.40, which we knew that it was 100, right? But I'm showing how it kind of relates. And then what about the probability you like Zoom? Well, that's going to be everyone in that bubble, right? That's the probability of liking Zoom. 0.25, 0.10, yeah, 0.35. Like Zoom. Well, then the probability you don't like Zoom, we're going to call it this complement. It's always 1 minus this, but probably you don't like Zoom is that you're not in that bubble. Okay, it's kind of hard to. If you're not in the Zoom bubble, 0.65. Okay, so a lot of probabilities going on with this. Now, what that rule stated before, though, it's the general addition rule. Yeah. The general addition rule says, look, what if you, okay, let me yeah. What's the probability you're a freshman or you like Zoom? Okay, you're a freshman or you like Zoom. So this means we could be in the freshman bubble or we can be in the Zoom bubble. Okay, now look, I'm going to kind of draw this with a pin here. So I can be in this bubble. That's the freshman bubble, right? Or I can be in the Zoom bubble. Okay, and the way you would add this up really is by saying the probability of being a freshman, so the probability of this entire bubble, plus the probability of liking Zoom, that's everybody in this bubble. But notice when you do that, you overlap the middle, right? All the freshmen plus all the people that like Zoom, when you add those together, you overlap that bubble. So you have to subtract freshmen and Zoom. Sorry about running out of space. And now go back, look, that's where this is coming from. This general rule for addition, that's where it's coming from. If you want the probability of A or B, you got to add A and B together, but then you subtract off the overlap. You subtract off the and. So for us, if I wanted a freshman or Zoom, I would say, well, the probability of being a freshman was 0.60. Plus the probability of being on Zoom, or liking Zoom, I should say, was 0.35. But then the probability of being both freshman and liking Zoom was 0.25. So this would be 0.7. Yeah, 0.7. Which kind of makes sense as well, because think about it. The only people that aren't in this bubble are the sophomores that don't like Zoom. And that's 0.30, right? So if 30% of the people are in this outlier area, that means 0.70 of the people have to be in either of the two bubbles, okay? So it's goofy. And I know this is goofy the first time you see it. And that's why I'm really spending a lot more time than your book does on it, because it's kind of hard to grasp. In my opinion, this is hard to grasp without the bubbles, okay? It's having that visual kind of explanation as we go along. And I'll do more of those. Your book doesn't. I'm going to do more of those Venn diagrams because it just helps doing it that way. Okay. So yeah, let's kind of go over a few definitions. I've only got you for like 2 more minutes. I don't think I can. I'm not going to. Oh, okay. It does go over a little bit of Venn diagrams here. The very top of page 220. Okay, good. So the next is a mutually exclusive event. Mutually exclusive. What that means is that these two events cannot overlap. Okay, they're impossible for them to occur at the same time. Two events that cannot occur at the same time. Like okay, and I'm going to tell you this because I don't want to go into some like long discussion about it on your beliefs or non-beliefs or whatever. But if we talked about like gender and statistics, gender is going to be a mutually exclusive event. You're going to be male or female. Okay, I know that there's other things you can be when it comes to gender, and that's fine. But for us to keep it simple in the class, we're going to say male, female. Okay. Or like if you're like the example we did a second ago, freshman, sophomore, you're either one or the other because you've completed 60 hours or 30 hours or you haven't completed 30 hours. And that's just the definition of a freshman or a sophomore. So those are good examples of mutually exclusive events. They're just two things that can't overlap. Then your book goes over Venn diagram. Look, I just got ahead of myself. Okay. And in a Venn diagram, a mutually exclusive event, there's no way it can overlap. Okay. This would be mutually exclusive events. So if you had like male, female, and then you wanted to look at something like, I don't know if you like Zoom or not, something, it's just a different way to write it. But then if you had things that could overlap, it would look like that. So, which is the examples we've done so far. These are not mutually exclusive events when you can have overlap. Okay. It's not a big deal. I'm not too worried about it, but it's a little easier when we're talking about mutually exclusive events because you can add them a little easier and subtract them. But because if there's mutually exclusiveness, if we have mutually exclusive events, because there's no overlap, when you add them together, so if you wanted A or B here, you could just add A plus B, right? You know, if we go back to our example from before, bring this up real fast. Because there's overlap, you have to subtract off one of the ands. But if we have mutually exclusive events, you just have to add the two probabilities together. So for this one, it would be like the probability of M plus the probability of F. Okay. Cool. I think it's pretty. I'm going to stop here. And what I'm going to do is I'm going to finish the lecture. I'm not going to give you any homework from 5.2. I want to finish the lecture first. So get that homework from 5.1 done, and then we'll finish up 5.2 tomorrow, or not tomorrow, but Wednesday. Okay. Do you guys have any questions online? So we'll finish up 5.2 on Wednesday. Not a big deal. Pretty straightforward. Let me stop this. I'll see you guys on Wednesday. I'm going to stop.
I do have a question. It's just not about the class.
Okay, yeah, that's fine. What's up?
It's about that project.
The project.
Yeah, for the honors program.
Oh, yeah. No, stick around, Zach. Let me stop the live stream. Hold on.